Hello, everyone. Good morning. And we have a special hangout today with Space India. And we're privileged to have here with us today Dr. John Mather, who's well known in the cosmology community. And we also have with us here, good morning, Dr. John Mather. Welcome to have you.
We've just been disconnected again. Okay, well, I can't hear you at the moment.
Welcome to Dr. John.
Okay. So we're having troubles here, but let me know when I should start talking. Okay. Well, students, I'm glad to be here with you and happy to tell you the story of the universe. We have the opportunity now because the world is now constructing this amazing telescope called the James Webb Space Telescope. It's an international partnership of 3 space agencies from NASA and Europe and Canada. And we are building this for launch in about a year or year and a half at the end of 2018. This is a telescope much larger than the Great Hubble Space Telescope, and coming up soon, we will see it. So this is a telescope that will be useful for everyone here on Earth. All of the astronomers in the world will use it. It's being built by several thousand engineers and technicians and at least 100 scientists worldwide. So can you see my slide now?
We can, yes. So we can't see your slide yet. So let me go ahead and introduce you.
Okay.
Dr. John Mather is a senior astrophysicist and the senior project scientist for the James Webb Space Telescope at NASA's Goddard Space Flight Center. His research centers on infrared astronomy and cosmology. As an NRC postdoc fellow at Goddard, he led the proposal efforts for COBE, Cosmic Background Explorer, and came to GSFC to be a study scientist and the principal investigator for the FIRAS on COBE. FIRAS is Far IR Absolute Spectrophotometer. With the COBE team, he showed that the cosmic microwave background has a blackbody spectrum, confirming the expanding universe model, the Big Bang theory. The COBE team also made the first map of the hot and cold spots in the background radiation, anisotropy. Dr. Mather is the recipient of numerous awards, including the Nobel in Physics in 2006 with George Smoot. Welcome, Dr. Mather. And yeah, let's move on to your presentation now.
Okay, well, thank you. I'm delighted to have a chance to speak with you. We have the story of the universe to tell you about, and also about the tools that we're using now to learn about it. What you see here on the first slide is a picture of the James Webb Space Telescope, planned for launch in October 2018, a little over a year away. It's being constructed by an international partnership of 3 space agencies, NASA, along with the European and Canadian space agencies. And it will be available for observers around the world, including people in India. You will have to write a proposal like everyone else, but you can use the telescope. So it's a huge project, very costly, very difficult, rather risky, although we think we've managed all of that. And so now I want to show you more about it. So what we have let me see if I can get my next slide here. I want to summarize the basic story of the universe and how did we get here from the Big Bang. So number one mystery, still a mystery to all of us, is that quantum mechanics determines the properties of everything, from the subatomic particles to the DNA that makes up our
Yeah, looks like viewers, we just lost John Mather's connection for a moment. So we hope to have him back here right now. And he's joined us back. Yeah, hello, Dr. Mather, we're back. Yeah.
Yes, we're having trouble with our computer. Surprise. Right. So the story here is, how did we get here from the Big Bang? Quantum mechanics determines the properties of everything. You all know that the expanding universe started out smooth and hot. What people don't fully appreciate is that everything has been unstable ever since. There is no such thing as a steady state in the world. Everything changes, and energy can be released by simple things reorganizing themselves into complex systems. So in particular, gravitation can cause the almost uniform early material of the universe to turn into galaxies and stars and planets. So that makes it possible for us to be here. Another thing to appreciate is that the universe is probably infinite, that is beyond all measure, that it's very, very old, about 13.8 billion years, which means that even things that are very unusual and will still be possible in this enormous universe. So we are here even if it's very unlikely for intelligent life to occur on any random planet. So we're here because it is possible enough. Another remarkable thing for us to think about is what I call stored information. So we have language, we have many ways that we write things down, but we've just recently been discovering the method in which nature has done this through the universe, through the method of DNA that controls our cells, and also, of course, the equipment that decodes and uses that information to tell living things what to do. So it's not just the DNA with the information, it's the system that gives it meaning that makes it possible for us to exist.
Sorry again for the interruption. We hope to have him back in a minute. Yeah.
So I'm
back. Yeah.
Yeah. This is a very poor connection. I don't know what the problem is if it's on my end. Let me see if there's anything I have to choice about. I think my network is okay. I just don't know what's happening here. So at any rate, the stored information enables evolution. I write down survival of the lucky, because people used to say, as Darwin said, survival of the fittest. But we didn't fully appreciate how much chance is involved in that. And we now know that according to genetic information, the human population, although we have had ancestry running back for many, many, many years, the population of people looking like us was down to a total of a few hundred human beings, probably in southern Africa. And then we have expanded from that and grown out to cover the entire world. So the way that it works is living things and everything else have feedback loops. So if you're an engineer, you study how to control things on purpose with control systems that give information back, and we can use them either to stabilize something or to destabilize. So this is just a quick summary of everything that's known, and it's extremely profound, and I don't know how to really convey all that. But now let me show you something of my origin story. This is the farm in northern New Jersey where I grew up. This is a research station for cows. So in the objective here was to make healthier cows that could give more milk. And so my father
So bear with us, viewers, because there's something wrong with the network.
Yeah, I don't know if it's mine or yours.
Yeah.
I have, I'm sorry this is a problem, but I do actually have another computer I could try. And so maybe we'll try that as well. So I think it's worth a moment to try to see if the other one will work any better. Who knows? But anyway,
yeah, we can have.
So I'll hang up with the one and try the other one.
Yeah, we can try that. Okay, so we see John on another call right now.
Yeah. Okay. So,
Okay, we have a feedback, so I'll.
yeah, let me switch my headphone here. So we disconnect from one, try the other. And just a moment, I wasn't planning to do it exactly this way, but let's see what we can do. So I'll try a screen share again to this one. So do we see that? Do we see my slide share again? Okay, you see me? You can hear me?
Yes, we can see you clearly. Oh, the slides are great.
Okay, maybe this will work better. Okay, so I was telling the story of this is where I grew up. Scientific research was going on in that farm, but I'm sorry we've lost a little time with the computer trouble. So wanted to point out that we all are able to look back in time as we look at things that are far away. And so as the light has a definite speed of 300,000 kilometers per second, we now can look at the universe and survey it, and we say we are able to look back in time tremendous distances by looking out tremendous distances in space and time at the same time. So we do this by surveying, as we learn in school. If you know one side of a triangle and two angles of the triangle, you know the entire space shape of the triangle. So this is basically surveying. And I think all of you would be able to do that too. The other method that we have is called the standard candle method. And we can do that by comparing the brightness of things, and when you observe the relative brightness, you say, well, if the faint thing is probably farther away. So this is called the inverse square law, and the subtlety of it is about the argument that those two things are really the same kind. So back in the early, late 19th century, it was recognized that we can measure the speed of motion of things coming toward us or going away from us by an effect called the Doppler shift. So each different atom or molecule absorbs or emits radiation at particular wavelengths of light. And so if you spread out the light of a star to make a beautiful rainbow, you'll see the chemistry of that star revealed in the particular details of this color. So the sun has particular dark marks across the rainbow that you can see with a good optical instrument, and they tell you what's in the sun. If you see another star, you say if it's similar but fainter, it's just farther away. But we'll often see that the wavelengths are all systematically shifted, either towards shorter wavelengths or longer wavelengths, and that tells us that a thing is coming toward us or going away from us, and we can measure the speed of motion. So in 1929, Edwin Hubble, who's shown here at the focus of the great 100-inch telescope in California, is shown measuring the motions of distant galaxies. So here we show a graph of the motions that he accumulated. On the horizontal direction is the distance that he estimated in astronomers' units called parsecs. In the vertical direction is the speed of motion away from us. And you see that there's a very remarkable trend in this plot that when the galaxies are far away, they're moving away from us at rather tremendous speeds. In this chart, almost 1,000 kilometers per second. And if you divide the speed of motion by the distance, you see the slope of this line, and the distance divided by the speed is actually the apparent age of the universe. So you can say it's as though we all started together, all the galaxies were together about 2 billion years ago. Oh, that was the number that he got, but it was in fact an incorrect number. Because the candles that he was comparing were not really the same nearby and far away. Nevertheless, in 1929, this was the first evidence that we had that the universe is actually expanding. It was a huge surprise to almost everyone. except for two mathematicians who had used Einstein's equations to predict this fact. But Einstein himself did not expect it. He believed that the universe must surely be static. So that was a big mistake on his part. But nevertheless, now we know that the universe does expand, and this is not something that we just thought would be cool or fun to have. This is the observations forced us into thinking about the expanding universe. So the next prediction from that expansion story is that the universe must have been very hot when it was young, and that must have been cooling off as it expanded. So the heat of the early universe must still fill the universe. So the objective then was to measure that heat very carefully. So it was discovered by accident in 1965 that this heat exists. And shortly after that, I was a graduate student looking for a thesis project in Berkeley, and we made an attempt to measure this heat, and it failed, actually. But nevertheless, I got a job at NASA. And when NASA said they wanted proposals for new satellite missions, we said, we'd like to measure this cosmic heat, and we have an idea. So 15 years later, this satellite, the Cosmic Background Explorer, that Mila Mitra worked on with me, was launched into space. And it immediately succeeded in measuring the heat of the Big Bang, as we call it now. And this next chart here that I show you is called the Cosmic Background Spectrum. So it's a measure of how bright this cosmic heat is at each different frequency. And you can sort of see the bottom scale there is measured in cycles per centimeter. So right in the middle of the picture is a wavelength of about 1 millimeter. So the theoretical prediction is the smooth curve. All of the measurements are right on the curve. And so this confirms what we call the Big Bang theory, or should call the expanding universe theory, to extraordinary accuracy. So a couple of years later, we made the second remarkable discovery with the Cosmic Background Explorer satellite. And this is a picture of that. The picture to think about is the one on the lower right-hand corner, which is a map of the entire sky. And these colored patches on this map represent that the early universe is just slightly hotter in some places and slightly cooler in others, just 1 part in 100,000. So when Stephen Hawking saw this chart, he said it was the most important scientific discovery of the century, if not of all time. And I didn't know yet why it was so important to people. We were just very proud that we had made the measurement. But the measurement shows us that, number one, the early universe is sufficiently non-uniform, that the gravitation of the dense regions is able to stop the expansion and turn that expansion of the material around and cause collapse into galaxies and then stars and eventually planets. And we're here walking around on Earth because those spots are on that map. Eventually, we might understand what made the spots, and that would be another tremendous leap forward for science. So here is a summary chart of the early universe. It was very, very hot, very compressed. It had no center that we are aware of and no edge. It's infinite. So it's an infinite universe expanding into itself. And that means also there is no first moment. If you try to imagine the movie of the expanding universe running backwards, you cannot actually get to the first moment. What happens instead is you get to extreme conditions and you have to say, I no longer know how to go farther back in time. It means there is no first moment, there's no instant of creation, and this expanding universe that we're describing is really not a big firecracker. And the Big Bang name that we've given to it is a terrible name. But at any rate, that's what we have. So we have the expanding universe. So how are we going to know if this picture is correct? Well, we have to take pictures. So we observe the universe with telescopes. This is a beautiful picture made with the Hubble Space Telescope. They decided to point the observatory in one single direction for several weeks and just wait for the light and photons to arrive from the distant universe. The picture shows you thousands and thousands of galaxies, including little tiny specks on this picture. And when astronomers saw this picture, they said, not only is this picture beautiful, it tells us things we did not expect. Number one, there are many more galaxies than we thought would be there. Number two, the most distant ones that we can see in this picture are still not the first ones in the universe. We built a wonderful telescope and it cannot see the first stars and galaxies forming. So a conclusion was, please build us a telescope that's even more powerful than the Hubble Space Telescope, and maybe we can see the very first galaxies forming by looking far enough away in space that we can look back in time to when the first galaxies were just being born. So we're now doing that. That's the biggest reason we're now building the Webb telescope. So here's an example of a nearby galaxy called the Whirlpool Nebula. You've probably seen this picture before, but this is a collection of hundreds of billions of stars orbiting around the common center. You can see the different colors that are due to different processes happening in the galaxy. The pink regions are regions of new star formation. The dark bands are dust clouds obscuring our view. And the blue regions are bright new stars. New stars tend to be blue because they're very massive. In the lower right corner of this picture, by the way, is a sketch that was made by an astronomer in 1845 who had a very large telescope in Ireland, and he was a good artist, and so he could see the same picture that you can see with the big telescope, even back in 1845. Another picture we took with the Hubble is this one. This is called the Crab Nebula. So the Crab Nebula is an expanding remains of an exploded star. It happened on July the 4th of 1054, the year 1054, which we know because astronomers wrote it down, and we still have records from China. And we think that we know what they meant, so it was the exact day that it blew up is known. It was so bright that you could see it in the daytime. And so it was a very, very important event for astronomers. Now we know that it's important for us in a much more personal way, because stars like this produce the chemical elements that make up the Earth. The original early universe gave us hydrogen and helium. Stars that blow up give us the other chemical elements, the carbon, oxygen, nitrogen, calcium, phosphorus. Everything that makes up the world that you see around you was produced in stars that exploded like this. And the atoms have been completely recycled by traveling great distances through the universe. So that's how we think it started. We also have now recently gotten a picture of a brand new star forming planets. This is a picture taken in South America with a special radio telescope called the ALMA. What we're actually seeing here is the heat emitted by dust grains orbiting around the new star in the middle. So this looks so much like the rings orbiting around Saturn that we think that we know what it means. And so the dark regions are thought to be places where new planets are growing. And if this is a new solar system growing like ours, it will have about 9 planets. This is a confirmation of our hopes and dreams for a long time, that we'd really be able to learn something about how solar systems can be born and grow and eventually produce planets with people. So that brings me to the new telescope, the James Webb Space Telescope, which is named after James Webb, the person who went to President Kennedy in the United States and said this is what it would take to get astronauts to the moon in less than 10 years, and he made that happen. So we've named the telescope after him. The telescope itself is extraordinary engineering accomplishment, and what we see here in the picture is a golden hexagon, which is 6.5 meters across, much larger than the rocket that will carry it into space. It's protected by 5 layers of a big umbrella, which we call a sun shield in the picture, and it is going to be launched into space next year. So it's, as I mentioned earlier, an international project with Europe and Canada. It has 4 instruments in it that take pictures and make spectra, which is to say those beautiful rainbows, to learn about the chemistry and the motions of the things that we see way out there. So it's going up on a European rocket called the Ariane 5, and it will be launched in South America in late next year. So why do we want to study infrared? This new telescope is special for infrared. So number one, we can see farther back in time. When we used the Hubble telescope to make that picture I showed you, we saw that we could not see far enough back to see the first galaxies because the wavelengths that we wanted to observe are too long for that telescope to pick up. We want to see things that are too cool to emit visible light. There are a lot of things that are too cool to do that. Here on Earth, you're transmitting 500 watts of infrared power out into the room around you. And so if you were in outer space, we would be able to pick up the heat that you are emitting, even if you are millions of miles away from Earth. Another thing we want to do is to see inside the beautiful dusty clouds where stars are being born. Because light behaves as a wave, it's possible for the longer wavelengths of infrared to go through the dust clouds and see inside. Chemistry, we can see molecules vibrating because they vibrate at lower frequencies and longer wavelengths than what you see from individual atoms. And finally, we do it because you can't do it from here. The Earth's atmosphere is opaque and the telescope glows with its own heat. So please build us a telescope in outer space to do infrared astronomy. So here's just one example of what we're doing to test the telescope. We have a gigantic vacuum tank in Houston, Texas, where the human space program used this same tank 50 years ago to prepare astronauts to go to the moon. This telescope has a diameter of about 20 meters and a height of about 40 meters, and it's big enough to put the telescope inside with all of its test equipment, and we are about to find out that it works the way that it will work in outer space when it's cold. So we're putting it 1 million miles, 1.5 million kilometers away from Earth, around a place called the Sun-Earth Lagrange point out here, the L2 point. So it's 150 million kilometers from the Sun to the Earth, only 1.5 million kilometers from Earth to the Lagrange point. So this is a good place to put an observatory because the observatory can stay there all year long without having to use much fuel. The observatory is so sensitive that if you were a bumblebee, a single square centimeter floating at the distance of the moon, we would be able to see you. Both the sunlight you would reflect and the heat you would transmit. So we will be able to observe everything from Mars in the solar system on outwards. And if you're an astronomer, there's already a tool you can get from the Space Telescope Science Institute. So you can imagine what your target would look like when we could take its picture. So here are a few examples of what we hope to see. Nature has given us what we call gravitational lenses. The gravitational force of galaxies is capable of bending light from even more distant objects. And this little pink thing that we see in the upper corner here is actually the image of a much more distant galaxy that's been magnified and distorted by the gravitational force of all these beautiful nearby galaxies. So we'll see farther out in space. We will see things that are dark almost. This is on the left side, you see a picture of a small instrument that was used to take pictures of and look for very, very faint, very fuzzy objects. And they've discovered a galaxy which seems to be 99.99% dark matter, which means it's very, very hard to see it, but we know that it's got an enormous mass. And so that's a great challenge for astronomy to understand that one. We will be looking at clouds like this. This is a picture taken with the Hubble Space Telescope. And it's a beautiful picture, and it's a place where stars have just been born. If you could see inside that cloud, you would see them being born. And so we use the infrared. Here's the same place as observed with infrared from the Hubble telescope. And so you can already see that there are many, many more stars in this picture that you can see. And you can see through the dust clouds to the inside where the new stars are being developed. We will be looking at places in the solar system. Europa, which is a satellite of Jupiter, has been now known for many years that it has an ocean underneath ice. And it's now also known that there's little places where water vapor comes spouting out through the cracks in the ice. So at least some American congressmen have said this is something they really want to do too. So they would like us to send a probe to this place and find a place to land and understand whether that satellite could possibly have living things in the ocean under the ice. So that will be coming. After that, many, many more projects are possible. This is a sketch illustrating that astronomers would love to have a telescope even bigger than the one that we're now working on. And if you could build it big enough, you would be able to see little planets like Earth as little dots separate from their stars orbiting around way out there, and you could analyze them to see if they show signs of life. So that's in our possible future. I don't know when we will get to do it, but many people would like to do this. So I think it will happen sometime. And so within your lifetime, we will be able to ask the question and possibly get a positive answer that there is life on a planet around another star. So you have a chance to work on it. So I hope that you will consider that space science and space engineering are interesting challenges. And if you don't get to work on it in person, please help us by thinking good thoughts and pushing for us to accomplish great things. So let's stop here with the talk, and I'll be happy to have questions from you. I'm sorry for all the trouble with the computer, but we're back in business.
A very good morning, all of you, all the students, and we'd like to thank all the viewers, and we'd like to thank Dr. John for an enriching and enlightening presentation. So my name is Vikrant, and I am an educator at Space, and I really loved the talk, and I will be, so we have lots of questions from students. Dr. John, I would like to mention that there is a special birthday wish. We got to know that your birthday is on 7th of August.
Oh, yes, indeed. Thank you. I will be 71 years old.
Oh, wow. So school students are also wishing you great birthday. So happy birthday from Space Family in advance.
Okay.
And also I'd like to mention that today there are we have about 40 viewers we can see, but many of these are schools. So I was told that we have at least 280 participants representing various schools who are watching you and, getting excited about the Big Bang, So we have lots of questions, and I believe we have many people watching from across the globe, the entire planet, I believe, from USA yourself to Japan. So
okay.
At least I know this. So there's a question from Advait. He's from Balbharti School, Pitampura, that's in New Delhi. What was there before the Big Bang?
Good question, and no one knows the answer to that question. So if there was something before, it means that we'll have to learn new kinds of science to understand it. Nothing in the laws of nature that we know about today tell us really what to do when we imagine backwards farther and farther. So maybe that'll be your question.
Right. Thank you. We have the next question is, okay, students from St. Thomas School in Dwarka, that's also in New Delhi. He is asking, what is the difference between COBE, COBE and JWST, that is the James Webb Space Telescope? What they're finding about the Big Bang?
Okay, well, the COBE satellite measured the heat of the early universe. As we showed you the color and the map. The Webb telescope will be looking at individual objects, stars and galaxies that formed afterwards. So now we know how it started, and now we will try to predict and calculate what the stars and galaxies should be, and then we will observe and see if that's correct.
All right. And we have Ishita. Okay, we have a question on the geometry of the universe. It's by Ishita from IP School, Dwarka. Why universe is flat and not spherical?
Oh, there are several ways in which you could imagine the meaning of that question. You could imagine that the universe might be structured so that if you start off in one direction and just keep on going, you would come back where you started, as you do here on Earth. And you could also imagine that that's never going to happen, that the universe is curved differently. So measurements are telling us that the universe will keep on expanding forever, and that it is geometrically flat, which means that the sum of the angles of a triangle would be 180 degrees. Here on Earth, if you draw a triangle, it's actually made of curves, and so the sum of the angles is more than 180 degrees. But in space, it would be 180. So that's something we have measured, or at least we think we have.
Okay, thank you. We have, okay, I have lots of questions and I'm having trouble selecting them, so excuse me. So how many dimensions of universe are there? This is a question from Harshit from Balbharti Public School, Pitampura.
Okay, so we know everyone sees 3 dimensions of space, and time seems to be special and different, but we think of it as another dimension because Einstein showed us that time and space are intermixed. Then we have hypothetical additional dimensions. When we talk to the particle theorists who try to study all of the elementary particles, they can describe those particles quite well if we have a total of 10 or 11 dimensions. So these other dimensions are not like the spatial dimensions and the time dimension. If they exist at all, they seem to be very compact, so that they're as though they were curled up. So we'll never be able to see them as far as we know geometrically, but we deduce that they exist because of the effect on the particles.
Okay, thank you. And there's one more question. Prateek Chatterjee, he is from IISER in Mohali. That's also in India. Does the inclusion of the cosmological constant explain the presence of dark energy in our current universe properly? If not, what are the exact problems in modeling dark energy?
Oh, that's a long, hard question. As far as we know, the dark energy is interpreted as an acceleration of the universe as it expands. And so far, the observations fit with Einstein's formula perfectly. So Einstein said you could put this constant in the equations and it would be all right with him. So far, that matches the observations. But that only means we haven't measured everything. So the big question for scientists is, well, that's working right now, but in the past, was that the right formula? Maybe the acceleration was different from what Einstein's formula would say. So that's the next big step for astronomers, is to measure that change of the acceleration with time.
Yeah. Dr. Mathur, you are muted somehow. Okay, now it's
no, he's fine. He's fine.
Okay, I'm back. I'm here.
Yeah.
Madhu Jha, one of the educators at Space, she is asking, what is the effect of dark matter and dark energy? Okay,
both of them have effects on astronomical objects, and no other effect has ever been discovered. In other words, neither dark energy nor dark matter has any effect locally here on Earth that we can see. The dark matter has gravitational force, and it can affect the way that things orbit in space. It can affect the bending of light as it goes through space. And it is probably responsible for our existence, even though we don't see it. Because most of those spots that I showed you in the map of the cosmic background temperature are caused by dark matter. So this is a big surprise for people. We're very hopeful that some year we may have an experiment in a laboratory that will reveal dark matter on Earth, but that will still not necessarily answer our question, because who knows if that's the only kind. So we have a very hard scientific problem. The dark energy is just a name that we give to the fact that the universe is accelerating. And it's very unknown. It was not predicted from any previous reasoning, so we don't know why it's there.
All right. Next question is from Chitra Khatri. How are galaxies arranged in the universe? So I chose this question because I believe the cosmic microwave background radiation has has some role in explaining this as well.
Yes, indeed. Well, the galaxies are no longer randomly distributed because gravitation has pulled them together. So we start off with an almost random distribution of the hot and cold spots in the early universe. As far as we can tell, that is completely random. But nevertheless, when we simulate the effect of gravity operating on those hot and cold spots, almost immediately the universe divides into small condensed regions. So there are individual galaxies, and they are grouped into great strings and even into great flat sheets in the universe, and the rest of the space is empty. So gravity does this, and so it's a remarkable, remarkable effect.
Thank you. This is a question from DAV Public School, Chennai. Chennai is in the southern part of India. The question is, Europa has water. Does that mean life can exist in Europa? This is from Prabhakaran.
So, of course, we don't know. But life seems to exist on Earth everywhere that it's wet. Everywhere that there's liquid water, there's life. Unless we go to great effort to make sure that it's not there. So in the hottest regions of the volcanic activity under the ocean, in the coldest regions under the ice, there's always life here on Earth. So we imagine that it would be possible on Europa, but we don't know. So the clear objective is go look, have a measurement, and see what's there.
Okay. Now there's a question about what will be the end of the universe. This is from Akshay Goyal, Rukmini Devi Public School.
Yes, okay. The prediction is that the universe will continue to accelerate and the distant galaxies will all run away from us. So in another 10, 20, 30 billion years, the sky will look almost empty. And so that will be a difficult time for future astronomers. They will not know the history because there will be nothing for them to see. Right. So that's the prediction. But in truth, no one knows why this acceleration is occurring. And that means we really don't know whether it will always continue. Right. So maybe it will change. One of the popular theories has always been that the universe expands and then contracts and bounces and starts over again.
Right, thank you so much. So what are the prospects of using gravitational waves in studying the very beginning of the universe, as we can only see light after the universe cooled enough? Did you get the question?
Yes. There is a possibility of measuring the gravitational waves. And so they are like light waves, except they are gravitational force moving through space. And prediction is that they must have existed in early times and that they must have influenced the particular shapes of those hot and cold spots that I showed you, and in particular producing a polarization effect. So many, many hundreds of astronomers are now trying to measure that effect. So in the 10 or 20 years, we might know. There is even a remote possibility that we'll be able to measure those gravitational waves directly with equipment. At extremely low frequencies, from timing the pulsars and various other strategies people have, there is a possibility that we can have a new kind of astronomy based on the gravitational waves.
Okay. We have Roheb, one of our educators. He's asking on behalf of a student. It said universe had a big bang and it started from a point of singularity or cosmic egg. Where was this point or egg situated in the space itself? Started from the, where did it all start? Where was this Big Bang happen?
Okay, that is a question that actually does not agree with the story that I told. I said the universe is infinite and is expanding into itself. And if you imagine running the story backwards to where the universe is more and more condensed and hotter, eventually you come to a condition that you cannot describe because it's just too intense, and we don't know the laws of physics. So we imagine in this story that the universe is still infinite even when it's very young. And we don't know why it began expanding, but that's our idea. So this means that the location of this cosmic egg is everywhere. The universe is infinite young, and it's not infinite now. So, so the idea of a singularity is a curious one. Infinity is not a place you can go to. Infinity is a name we give to not being able to go there. Infinity means beyond all limits. So this is tricky for people. Infinity is not a place. How was that?
Yeah, that's good.
Thank you. That's quite enlightening. Okay, yeah. Yashaswini from IP school, Indraprastha School, Dwarka. Did time go slower just after the Big Bang?
We define the speed of light based on molecular or atomic vibrations, and so in our modern science, the speed of light is a constant for sure, because that's what we said it is. We measured it, and then we decided to call it a constant. And so, in that perspective, the speed of light is always the same. Now, we could easily say, well, the properties of other material might change. So maybe the masses of the particles might change, or other things might change with time. And we've been looking for that effect. We'd like to see if the distant galaxies have the same chemistry and the same quantum mechanics and everything. And as far as we can tell, they do. There is no way that we have yet found any change of basic laws of nature with time.
Okay, thank you. Okay, we have more questions coming up. Actually, my screen is full of questions.
Okay, good.
Madhu Jha, she's asking from GD Goenka School, Sector 22. She's one of the educators. Does the multiverse exist? How is it linked to Big Bang?
So, does the multiverse exist? It's actually not something we could ever know. We have mathematical ideas, and they might be true, but we would never be able to verify them because we can only see this portion of the universe that we live in. And so no one has yet suggested a way in which the multiverse could have a direct effect on the universe that we see.
Okay.
Do you have any more, Vikrant?
Yeah. Sorry, I wasn't able to hear Dr. Mathur now. Swarit Singh,
okay.
Will the universe continue to expand indefinitely, or is there enough mass in it for the mutual attraction for its constituents to retard the expansion and finally bring it to a halt?
So right now the measurement says no, we do not have enough gravity to make the expansion stop. And in fact, it seems to be going faster and faster all the time.
Okay.
So that's what the measurements are showing us, and it was a big surprise. In fact, people got the Nobel Prize in 2011 for that discovery.
Okay. Okay, one more question is there. How does the space-time continuum affect the movement of celestial bodies?
Oh, well, the space-time continuum is just a way of describing the motion. So as far as we know, the space-time is a description rather than a thing. So space-time is not made out of something else that we can yet recognize. So we know space is not actually empty. There are particles zooming around. There are quantum mechanical fluctuations in empty space. So people say, well, that's the properties of space. But we honestly have not seen anything that would say space is made out of something. Space is just a description. And so we say it's expanding, but that doesn't actually mean very much. We have to go think about what it means. So I wish I could answer your question better, but there's no, not much effect.
Okay. I have there are more questions with me, and if we have time, Mila, I'll go ahead. What do you think?
Yeah, Dr. Mathur, can you be here for another 5 minutes or?
Yes, I can. Yes, thanks.
Okay,
So
yeah,
my question is, when we talk about cosmic microwave background radiations, it said that the CMB would have crossed the Earth, from nearby places, but we can see cosmic microwave background from distant universe. So is there the closest edge of these radiations which we can see from beyond onwards? We can see. So is there a closest place where we are getting the cosmic radiations?
Oh, okay. Well, the universe has been transparent for most of its history. So the cosmic microwave radiation has been traveling freely through space beginning when the universe was about 400,000 years old. Very young by comparison to current age of 13.8 billion. So we see the universe by looking out in every direction and seeing the cosmic background radiation that is arriving from every direction to us right now. And we see it as it was when it was last bounced off of some electron. So that's how we look back in time that far. Nearby things, we see them with different wavelengths. So we see the sun and the stars and the planets at different wavelengths. But the cosmic microwave radiation does not come from nearby because the universe is transparent.
Got that. So I'm looking for more questions here. Sorry, just give me a moment, please.
Okay.
You have more questions?
Yeah.
So, Mila, I'm finding questions. If you have something, please go ahead.
Yeah. So let me also look.
Okay, I have one. Okay, this is a different one. Roheb asks, tachyons travel faster than the speed of light. How is this and quantum teleportation? How this and the quantum teleportation can help us in our future endeavors? So this one is about tachyons. I hope that will interest you.
Yes. So far, no tachyons have been observed directly.
Okay.
They are an idea. And so we don't know exactly how to interpret the idea since we have no observations. But quantum entanglement is very fascinating and once in a while appears to mean that information is being transmitted faster than we think it should be. But just I want to remind you of something rather puzzling and surprising, which is that if you travel at the speed of light, then time does not exist for you. So if you could travel really, really fast, time would slow down. If you could travel at the speed of light, time would not exist at all. So the idea of simultaneous events is really very well understood in relativity theory, but it's still always surprising to us. So just as a reminder that time is not so simple after all.
That's right. We have a question from Prabhakaran. What is your take about our technological development for scientific exploration? And how do you see evolution of scientific exploration from Einstein till now? Did you get that?
Oh my goodness, yes. Well, there's an enormous acceleration of discovery recently because of new equipment that we can build. Because now the entire world is participating in scientific exploration. The huge investment we've made in electronics and computers and software has enabled us to build things we never could have done before. And of course, the space race and the arms race have compelled us to do things we never would have wanted to do before. But they've made the possibility of these new discoveries very, very real. So as long as we have a very powerful, wealthy international trade in every possible thing, there's this huge amount of resources available for scientific discovery. I think there's almost no limit to how far we can go. My perspective is that if it can be discovered, then it will be discovered. If it can be invented, then it will be invented. And ideas will continue to grow. So I think the answer that I'm giving is both optimistic and dangerous. So do we have more questions?
We have a couple more.
The
Okay.
universe, okay, Roheb, one of the educators, is asking, this is, the universe is 13.8 billion years old. Still the size of observable universe is 96 billion light years. Kindly explain this. GD Goenka Public School, Sector 9, Rohini.
Yes, okay. There's an interesting concept here, which is that the universe that we observe with our equipment is no longer the way that it is observed, because time has passed. When we look back to see the cosmic microwave background radiation coming to us, it's traveled for 13.8 billion years. That material has now moved on. It is now different. It has turned itself into galaxies and stars and planets way out there. And in the same time, it has also moved. It is far beyond the place where we see it. So yes, it's possible because the material has been moving since it sent the light to us.
Thank you.
Yeah, Mila, that's it.
Okay.
Okay. Well,
So,
thank you all
yeah,
for coming. I was really pleased to get a chance to talk with you. And Mila, thank you for inviting me to talk.
Yeah.
Dr. Mathur, I would like to say thank you to you. It's been very enriching talk, and especially about this topic, which fascinates us all. So really, thank you so much. And I would like to thank all the schools as well. Over to you, Mila.
Yeah.
And everyone who joined.
Again, and thanks from my side and on behalf of Space to Dr. Mathur for joining us today, because as Vikrant mentioned, we have a lot of schools and viewers here with us today, and they got a chance to talk to you and find out about cosmology that fascinates all of them. So hopefully we can have you back with us sometime. And thank you, Vikrant, for co-hosting. So for your fascinating questions, and we're sorry if we couldn't get to all of them, but hopefully he gave us a broad enough perspective that we will get the overall picture. Thank you again, all of you, and good morning, and good evening, good to you. Thank you.
Okay. Thank you, and bye-bye now.
Bye.